Okay, so our 15-year-old is getting very ambitious and has decided to include humidity. Now, it doesn't really make sense to talk about maximum humidity during the day. I don't think so. So what the 15-year-old decided to do, is to measure it at 3 p.m., which is when you get home from school. So what we're going to talk about is the temperature, to the maximum temperature during the day, and the humidity at 3 p.m. All right, so we'll put barometers out at all the places where there are thermometers and do the same kind of thing. But again, there will be a forecast of humidity for that day from the newspaper. All right, so, but now we've got two variables, temperature and humidity. I'm going to use the variable S for humidity because H has a special role in data assimilation, so I don't want to use that. So think of S for saturation. Okay, so we're going to assume that X minus the forecast is distributed now, and now it's a two-dimensional variable, so this is a multivariate PDF, normally distributed with X minus XF, normally distributed with mean 0, and we have to specify now a covariance matrix, a 2x2 covariance matrix B. And then X minus X0 is going to be distributed with a two-dimensional covariance matrix R. Okay, so B is like sigma 1 squared, R is like sigma 2 squared, but they're 2x2 matrices. So what you want to think about, first of all, is how you're going to figure out B and R. Okay, well, you basically do the same thing as before, and you could imagine making sort of a histogram, but now it is a histogram in two dimensions, right? Because there are two variables, and so you will have a histogram with base space being two-dimensional, and basically forming the variance in the same kind of way. But if you think about it in 2D, you have to think about exactly what it is, but it's called the sample covariance because you're using it. You're using a sampling of your distribution, which is what you're using to form the histogram. If you want to look up what that is, there's a nice simple YouTube video which explains it very nicely in exactly 2 dimensions. And then you're going to do exactly the same thing for R, right? You're going to do a sample covariance. Okay, so now let's think about applying our two different approaches. We've got the interpolation approach and the optimization approach. So it's really generalizes in a very simple way. We just got vectors now instead of scalars. K is going to be a 2x2 matrix here, right? So it's going to be just the same formula as before, but there's a 2x2 matrix. What if we do the optimization approach? Again, we got X minus XF normally distributed, X minus XO normally distributed. What is J of X going to be? So that's sort of a question. I will assume that B and R are invertible. And then the question is, what is the functional that you're going to try to minimize? Well, it's just now it's a vector instead of being a scalar. You're sort of base space, but you can still write out a quadratic. I'm going to use these parentheses for the inner product, and so what you do is you take X minus XF, B inverse X minus XF. That's sort of the complete analog of 1 over sigma squared times X minus XF squared, right? But X is now, well, we did have T minus TF, X is now a vector, right? And then plus X minus XO, comma, R inverse X minus XO. Okay, O again stands for observations. So that's exactly what your J of X should be. Let's write this out in a slightly different way because it's kind of useful. If we write it out in matrix notation, it's X minus XF transpose B inverse x minus xf plus x minus xo transpose R inverse x minus xo. It's a useful form for writing it out. So the question is, can we again see that the formula which we get from the interpolation approach is exactly the formula that gives us the minimum of the cost function? Okay. So in other words, can we choose k so that xa, given by this gain formula, the interpolation approach, minimizes j of x? All right, so that's a question of, again, this is a quadratic cost function, so it should have one minimum. So we just want to find where the derivative of j is equal to 0, the gradient of j is equal to 0. The following formula will be useful, and that is that if A is symmetric, then the gradient with respect to x of x in a product ax is exactly 2ax. Okay, it's that vector, it's a gradient, it should be a vector. Okay, so now what we want to do is we want to calculate the gradient of j of x. Okay, well, I'll leave you to do that for a sec. You can pause and try to figure that out. Okay, we're using this formula. It's now not hard to see that this is equal to 2b inverse x minus xf plus 2r inverse x minus xo. Okay, and now what we want to do to find the minimum is to set that equal to 0. Okay, you can cancel the 2's and you can collect the x's on one side, and you get b inverse of x plus r inverse of x is equal to b inverse of xf plus r inverse xo. If you go back and look at our formula that we did in the one-dimensional case, that is really completely analogous, and you now get that x is equal to b inverse plus r inverse times applied to b inverse xf plus r inverse xo, right? So now you can see that you could multiply this through and you've got exactly a formula where you've got a sort of weighted average. And again, you can try to find an interpolation from this, and you will see, if you work this out, that k is equal to b times r plus b inverse. Right? In other words, so xa is equal to xf plus b times r plus b inverse times x0. Right, which is completely analogous to the one-dimensional case, but now with matrices instead of scalars.